Hello and welcome back to Beyond the To-Do List, a podcast about productivity. I'm your host, Eric Fisher, and in this episode, I'm excited to welcome Ben Orlin, author of Math for English Majors, a human take on the universal language. He's an educator, a writer, and has a book series that makes math more accessible, humorous, and relatable. And in this conversation, we are talking about how to understand math as a language, as a form of communication, and getting over some of the stigma and negative experiences that, like me, you may have had with math in school. But Ben reframes it through storytelling and humor and makes math more engaging and approachable. And then how that relates to productivity is this concept of stuckness. We've all been stuck at a point in a math problem. Sometimes, as you'll hear in this conversation, mathematicians will get stuck for over 7 years and then some. But it's all about what you do in that stuckness, insights into how to flip and frame that problem-solving moment you're stuck in, as well as making better decisions because of it. So even if you love math, I think you're still going to get a lot out of this conversation with Ben Orlin. Well, this week it is my privilege to welcome to the show Ben Orlin. Ben, welcome to Beyond the To-Do List.
Yeah, thanks so much, Eric. Yeah, I'm really excited to chat with you.
Really excited to have you here. I never thought we'd be talking about math.
Almost everywhere I go, I get that, including in classes. Did not expect we'd have to do math today.
Why are we talking about math in our math class today? The student said. But you've got a book out called Math for English Majors, a human take on the universal language. And I'm very curious. You're describing math as a language. So I guess unpack that analogy for us. How does the perspective shift there help people to approach math differently, and why?
Yeah. So first of all, I want to say English majors is not meant to be an exclusionary term. It's been fun actually since the book came out, having so many people come out of the woodwork. People I didn't know majored in English, but they all come to me, I was an English major back in college. So that's been fun. But it's sort of really math for human beings, math for anyone. And yeah, as you say, the reason English major shows up in the title is that I wanted to focus on the language side of math. I think the glamorous side of math is when you're talking about huge numbers. That's the closest we get to glamour. You talk about how many stars are in a galaxy or how many atoms are in the universe. I wanted to focus on something a little humbler than that, actually, and especially kind of drawing on my experience as a teacher. What are the places where students get off the train? There's like a few stops on the train of mathematics where just the train empties out. And there's an early one, which is fractions. I see that so many students are just like, nope, I'm done with that. Numbers I was fine with, but one number over another number, and there's a million different ways to say a half. I don't like that. They get off the train. And then really the one where the train empties out is algebra, often around 8th or 9th grade when, and the way everyone always says it is when it's, I was okay with numbers, but the letters, I didn't want letters in my math class. That was not for me. And so it's a moment when even if people keep taking mathematics after that, often they're kind of checked out. Like they know this is not the path for them. They've kind of written it off in their minds. And so in both cases, it's the language that's throwing people. It's there's something written down on the page, and that thing isn't feeling like language to them. It's feeling like this inscrutable series of marks, and there's these rules you have to follow for moving the marks around the page. And it's almost like what I imagined sorcery would be like if sorcery worked. You've got to conjure just the right symbols in just the right order. It's like, kind of reciting like a Harry Potter Latin spell or something. And it all feels very mystical and strange to people. And I wanted to just kind of go through symbol by symbol almost and just unpack it. Like, what are we talking about when we write those letters next to each other?
Yeah, it's like understanding the components of a spell, I guess.
No, exactly. We're showing the spells aren't actually magic, that there's just patterns out there in the world, patterns that like my 1-year-old and my 5-year-old come across when they play with blocks or when they, draw little dots on a page. And we've got fancy names for those patterns and we use them to discover new things, but all it is those same patterns.
Well, for me, so one of the reasons why I never thought we'd be talking math on this show is because I guess I'd given math a stigma myself. I understood fractions, totally didn't have a problem there.
Sure. It was you were still on the train at that point.
It was high school and it was algebra. And it wasn't that I didn't understand that those letters were placeholders, but it's that I just couldn't get it to work or click in my brain. And I didn't really have either the courage myself to ask for help or the confidence in the teacher or teachers to ask them for help, but got through. I squeaked by, graduated high school, but then I needed a math course in college and took one my very last semester, barely failed it, barely. was allowed to walk with all my friends, but then I had to take a May term right after and make up that class. And then, of all people, one of the tennis coaches at the school taught that math class, and it clicked. He was able to get it to click. It kind of something fell in place. I got it, and then I was whipping through it, and I was doing it correctly. And as I was taking, I think, one of my finals, I was taking it over in the phys ed or whatever office, athletics office, and he was walking by, and I heard him talk. I mean, basically, I was able to tell him, "Hey, you were the one that finally helped me get this, and thank you so much." So that was a moment of stuckness for me, which I know you have. That was years long. Like, we're talking late 90s into early 2001 or something, 5-6 years of stuckness with math. But you talk about stuckness in the book. Talk a little bit about that and how that relates to math and how you talk about that in this book.
Yeah. Well, no, thanks for sharing the story. Yeah. Hear a lot of variations on stories like that. They're always interesting for me because, you know, math can be puzzles, and it can be games, and it can be kind of fun stuff, or it can be the series of hoops you have to jump through in your education to walk down the aisle and get to where you're trying to go. And yeah, it makes me sad to hear all those stories of people who got thwarted or got blocked on their path because of, you know, a mathematics course that just wasn't working for them. But yeah, so stuckness, right? I mean, I think it's a big part of math. And actually, the deeper you go into math, the more it becomes about being stuck. So, for example, I'm a teacher. My wife is a research mathematician, so she has her doctorate in math. And so lots of the folks I know through her are research mathematicians, which is to say, basically what they're trying to do is they're trying to solve a math problem no one has ever solved. You know, when I give problems to my students, I generally don't give them ones that no one has ever solved. They're mostly ones I can solve myself. But there's problems out there that build on old problems, or questions have arisen, like no one knows the answer to these. To me, looking at mathematical researchers is one of the purest models we have in society of what do you do when you're stuck? Because inevitably they're stuck. If you're working on a math problem no one has ever solved before, you definitely don't sit down and just be like, oh, I know what to do. I carry the one. There we go. We're done. It's going to take years. And so one of the famous examples I like to cite is a problem called Fermat's last theorem, which I won't give the punchline away, but this was a problem sort of first written down in the 1600s. And he was reading a book, and it was about Pythagorean theorem, actually. So about how you can take a square number, and often you can break it down into two smaller square numbers. So take like a 5 by 5 square, right? There's 25 little, if you draw like 25 dots, 5 rows of 5, you get 25. You can break that into, 25 can break down into 16 and 9. The 16 can make a little 4 by 4 square, and the 9 can make a little 3 by 3 square. It turns out you can do that with other squares too. And so what this guy, Pierre de Fermat, writes down in the margin, he's like, oh, you know what? You can't do this with cubes. You can never take a cube and break it into 2 cubes. And so on for 4th powers and 5th powers, 6th powers. Anyway, he writes that down. He says, and I know how to prove this is true, but I'm writing in the margin here. It doesn't quite fit in the margin. Can't quite fit it here, but I've got a great proof of this thing that I just claimed is true. I just can't quite write it down here. And in hindsight, it's clear he did not have a proof. But what happened is this problem was published, he sort of left it in his papers. His son published it, 40, 50 years later. And then the human race was stuck on it for the next 300 years. It was a problem that mathematicians kept working on, kept thinking about, and just couldn't get over it. They make a little progress here or there. They'd sort of solve it for some of the cases, but they were trying to prove this thing he'd written down in a margin in 1638. And here we are rounding into the 20th century, and nobody solved it. Nobody can find the proof. And then finally, it's this guy, Andrew Wiles, now Sir Andrew Wiles, thanks to his work he did on this problem, who gets tenure, which I think afforded him a kind of protection. And then he goes up to his office in the attic at his house, and he spends the next 7 years there just working on this, just trying to find a path. At this point, it's connected to other problems. So he's doing kind of rich, interesting work. And he knows that even if he doesn't solve this problem, it'll still be worthwhile. Anyway, 7 years go by, and he's not up there the entire time. He comes down for dinner with his family. And then finally he emerges at the end. He says, I've solved it. And it turns out he's wrong. There's a mistake in there. But then another year goes by, and he works with a friend, and they solve it. And so finally he's able to publish it. And now it's no longer Fermat's last theorem. It's the Fermat-Wiles theorem. And so, this is like he's now, we don't have famous mathematicians. That's an oxymoron. But the closest thing we had in the 1990s was Andrew Wiles. He was sort of, there was a BBC documentary. There were books written about it. It was this really celebrated problem. Anyway, and the reason I love the story is just that we were stuck for so long. We knew what the problem was. We knew what the answer should kind of look like. And it still took, most of 4 centuries for, and it wasn't just Wiles, obviously. He was building on the work of hundreds and hundreds of brilliant people who had come before. to get an answer there. So anyway, that's why I like to think of math as a model of like, what does it look like intellectually? What do you do when you're stuck on something? How do you be productively stuck?
Oh, that's a really good question. Productively stuck is not something I think anybody's ever said here, but obviously that's the problem we're all trying to solve with everybody's dialogue on productivity in and of itself. Oh man, it's a great perspective to have. I can't get over the 300 plus years and then he decides 7 or 8 really to work on it and dedicate to it. And obviously not sitting there the whole time, but what else was he doing during that time? I mean, was he doing anything else? I mean, obviously the tenure allowed him freedom.
He was at Princeton or possibly the IAS, the Institute for Advanced Study. If he's at Princeton, then he would have had some teaching requirements. I'm sure he was teaching a few classes in the time, probably teaching some classes for grad students. But yeah, I choose to retain the romantic image of him just, every day he gets out of bed, he has a little breakfast, a little coffee, goes up to his office in the attic and just works and works and works, comes down for meals. I'm sure it wasn't quite 24/7 or even, 8-5 or whatever, but I think it was pretty much his singular focus. I know that within the math research community, there was a sense of like, where's Andrew? What's he up to? Where'd he go? Like, he hasn't been publishing much lately. Is he? Oh, I hear he's working on that problem. And part of the reason he chose that one, I've heard him speak about it, and part of the reason he chose that problem was he knew that even if he didn't get it, it had been, when it was first stated in the 1600s, it was kind of this little puzzle. But over time, there had been connections drawn between that problem and other important problems. So really, he was working on kind of other important problems in mathematics that happened to be connected to this one. I think he said if it were just that problem in isolation, it wouldn't have been worth putting 7 years in because, part of struggling productively is picking something where even if you fail at the stated goal, something of value will emerge. Mm-hmm. And so there are problems in math that don't fit that description. And so people don't tend to work on them. And then problems that do. And it's, it's okay to pour years of your life into them because even if you don't get the prize, you're going to get consolation prizes that make up for it.
Well, and a lot of people would say that even just the exercise of attempting over that course of that time, all the while probably teaching courses, but then I got my course, I went and I did FaceTime today and now I'm back in my attic and I'm working on the real problem that I'm working on. That all the while his continued exercise there, most people, if they were in his position, they would say something along the lines of, well, yeah, that's the problem I'm trying to solve. But in the meantime, it's helping me exercise my brain in ways that I hadn't or wouldn't have been doing up till that point. And so by taking on this challenge, creative choice here, that it's yielding other things in his other areas or other things he'd been working on, et cetera.
Yeah, I think to outsiders looking at mathematics, it feels like the products of mathematics are very rigid, right? Like you sit down, you do a calculation, you're producing that number we need, what is X or what is the area or what is the perimeter? And when you talk to mathematicians, actually, they don't really talk about it that way. They talk about the product of mathematics as being understanding. That all of the work they do is to try to find sort of logical pathways through hard problems and to crystallize an understanding of something. So, when you're working on a hard problem like that, if you don't know you're going to solve it, really what you're doing is you're learning. And learning is always valuable, even if what you learn is this is a bad place to explore. Don't go off the trail in this direction because there's alligators over there. That's still valuable learning as long as you don't get eaten by one of the alligators.
I think a lot of people would have a problem, though, with, oh, my gosh. I mean, if they'd known it was going to take 7 years, well, that's the thing. We never know how long something's going to take it when we're trying to do that. But again, going back to that word of stuckness and thinking of that as a crucial part of the learning, not just of math, but basically anything, I think is your perspective here. How do we embrace that? How do we handle it's like one part waiting, one part obstacle, one part do I have enough or rising to the occasion? Like it's a mix of and all that and more. How do we apply that?
Yeah. For me, I think foregrounding curiosity is a big part of it. If I look at a problem, whether it's, a problem I have in my career writing books or a math problem I'm trying to solve, and I'm looking for the achievement, I'm looking to accomplish that thing. If I accomplish it, that feels kind of nice. But if I don't accomplish it, it's enormously frustrating. And it can kind of wreck the day because I set aside an hour to do that thing and I didn't get it done. And if instead I view the goal as I'm setting aside an hour to learn as much as I can about this thing, or to try an approach and see if that works. And if it doesn't work, that's okay, because I'm still sort of accomplishing that. So maybe this is me being a very to-do list governed sort of person. But I find that just defining the goal in such a way that the goal is to explore, the goal is to engage my curiosity, the goal is to try something. And if I achieve that, then that's a check. That was an hour well spent or a day well done. And it doesn't have to be about accomplishing the thing, because I know that at the end of some long stretch of time, doing lots of those explorations or lots of those little intermediate goals will get me where I want to go.
Yeah, it's kind of those, putting in the reps leads you to something you weren't intending to originally, but getting there. Part of solving the problem is solving the problem you don't know you're even solving, and being open to that, I guess, is how I'm thinking of it in my head, at least.
Yeah, I think that's right. I see this less in math, I guess, and more in other parts of my life. But when there's something I'm being a little avoidant about, it's like, okay, I need to buy a wedding gift for that person. The wedding was 2 months ago, and I'd like to go buy a wedding gift. And then I'm just like not doing it. It's sitting there on the list of things I mean to do, and I just I bounce off of it. Usually what I need to do is I need to break that down further. So what I need to do is sort of open up that item. Okay, I need to buy a wedding gift. Why am I not buying this? And then if you're like, oh, the reason is because I need to have a conversation with my wife about what kind of stuff they might like, or I need to think about, I don't know, remember what did they get us for our wedding so that we can get them something that, maybe rhymes with that. There might be some other sub question, and I really need to solve that first. So often for me, and I think this is something maybe I borrow from math, when you've got a big problem, it can be paralyzing. And so you break it down into what are the steps, what are the questions along the way.
I hadn't thought about that in terms of always telling people, hey, well, the project is large and amorphous and unknown, and you don't know all the steps that are baked in or broken down in there somewhere. It's just this big behemoth of a thing. But once it's the whole joke, how do you eat an elephant? One bite at a time, right? But we don't know how many bites, and we don't know how big the bites are. And we don't know how big it's like, okay, but what? So pick one and do 2 minutes of research to know and define one aspect of it. And then suddenly it's like, oh, there's been so many times where I've procrastinated on something, and it's because I didn't know, I didn't define the parameters. And then, or I didn't take the time to take a couple of steps in and drill down and say, oh, this thing I thought was going to take 2 hours literally took me 20 minutes. And I wished I'd done it a month ago, but I didn't. And it's because you didn't, you just didn't start for 2 minutes or 5 minutes with a timer and then jump in, do as much as you can, figure out, oh, this is way faster and way easier than I thought. So we create an obstacle where there was none.
Yeah, as someone with a little mathematical training, I maybe overextend the mathematical analogies. But that's another one that I think I get from math, that you can have two problems that look almost identical. And it turns out one of them is really easy and one of them is really hard. So remember, there's a chapter in my second book about calculus, sort of stories of calculus, kind of fables of not really going into the technicalities, but just kind of the ideas and the history of it. But I show in one of the chapters sort of side by side two examples where there's one where, it's not an easy problem, it's a calculus problem, but it's a standard one that any student who takes a calculus course learns how to solve that. And then there's another one that honestly, I would never know how to do if I didn't use a computer. It would be days of filling paper and cranking through calculations. And all it is you change a 2 to a 3. That's it. Wow. It's just something is squared versus something is cubed. So they look to the naked eye, they look identical, but they're really different. And so I guess, one of the things I get from math is that you can't know at a glance always what is a hard problem and what is an easy problem. You actually need to sink your teeth into it a little bit. You need to kind of dive in on the assumption that you're going to solve it. And then you can start to get a feel for how vast or how manageable that problem is.
Yeah. And that's, again, with projects, you just don't know unless you've had experience with that type of a project before, so that you can define, well, this is typically what it takes for this, and, fill in the variable. I love using language and then filling in math variables for it. Speaking of which, you talk about math being a universal language. Why do you think that is the case? How does your book aim to help people understand math more by making it seem like we're all speaking it?
Yeah. So where algebra shows up in math is this funny time. And that's where math sort of starts aspiring to really be this universal language, right? By talking about variables and equations, we're going to somehow talk about everything, and you're going to use it in economics, and you're going to use it in physics and biology and chemistry and earth science. Every discipline is going to draw on this stuff. And you sort of think, well, how could that work? Right? What is there? If I'm writing down stuff about physics, the kinds of things I would say about physics aren't the same as the kind of things you would say about economics or the kind of things you would say about literature. How could one language serve all these purposes? And so what I try to show in the book is that math is incredibly useful for talking about some very specific things. Whenever you do math, you're ignoring a lot about the world. I think about this with statistics. So when you gather a statistic, say we're looking at the lifespans in different countries, right? It's interesting to know, like the fact that in Japan, the life expectancy for women is close to 90. It's like, well, that's kind of cool. Now, there's tons we're leaving out. We don't talk about how large the different generations are, right? If we're comparing two countries on that. And we don't talk about what you're doing during those 90 years. And we don't talk about how nice the birthday parties are. And we don't talk about, we're not looking at, I don't know, how do those 90-year-olds spend their day, or how healthy are they, or what's the medical treatment like? Like, none of that is in the statistic. We're just looking at the numbers. But the world is really complicated. And so boiling it down to numbers has a power, has a value. It's the bird's eye view. It lets you see things in sort of their broad sweep that you might miss if you're too focused on the details. And so what I try to show in the book is that that's what math is doing almost everywhere it shows up. Even when you're doing something simple as counting, counting marbles. If I count 5 marbles, you count 5 marbles. We're not talking about how cool the marbles are, like how nice are those swirly patterns, how big are they, do mine have cracks in them, do yours have cracks? Like, we're not talking, did I get mine from my best friend, did you just steal yours from me? Like, none of that shows up, none of that is in there. It's a very, very simplified picture of the world we get when we use a number. And so that's one reason I think math alienates people, is that they know that so much is getting left out. But it's also what makes math so powerful. It's sort of, sharpened like a knife, where it's just got this very precise point that it can make. And that's why math, I think on its own, doesn't get us very far in almost any walk of life. But it's a pretty useful tool in almost every walk of life.
You say that playing around is a way to discover insights in math. What are some examples of how that approach looks?
Let's say the book I did before this one actually was a book of like pencil and paper games. So like mathematical games. Sort of one of the more famous ones is this dots and boxes game, where you draw a little field of dots and then draw little lines connecting them. So I've been thinking a lot about mathematical play. I mean, there's a lot of sort of famous examples. Probability now is kind of one of the most important parts of mathematics, right? Probability comes up anytime we're not certain about things. Anytime we're less than 100% sure, now we're dealing with probability. And that's pretty much all the time. So, it comes up in financial markets, and it comes up in biology and physics and everywhere. And one of the early landmarks in probability was this problem just about a gambling game, where we imagine two people are flipping coins. So just playing a game, and they're playing, it's a pretty boring game, to be honest, to be just flipping coins, whatever. They're playing first one to win, I think 7 flips is the winner. And they get to the point where, I'm going to get these numbers a little wrong, but they get to the point where you're beating me 5-3. And then we have to stop. It's dinner time, whatever. Where you got to go, I got to go. And so we're stuck there. We don't get up to 7. And the question is, how should we split the winnings? Turns out that problem, just thinking about like, oh, we've been playing a game. How do we divide the prize? Was this really important problem in early probability. There are two, actually, Pierre de Fermat again and Blaise Pascal, who's the other mathematician he was corresponding with. There's this famous series of letters back and forth between them, where they're kind of bouncing around that problem, which their friend had showed to them, their friend who was like an inveterate gambler, and he had given them that problem. So just messing around with that problem is what led them to really foundational ideas of probability theory.
I'm still kind of stuck on the one problem where the guy was taking 7 years. The idea of most of us, we wouldn't know. I mean, again, he didn't know, and we wouldn't have known how long it was going to take to finally have that breakthrough moment. But that continually pounding away at the problem is going to be frustrating to people. What is this idea of, stepping away, giving the problem an incubation timeline for when it comes to solving these problems?
That's right. Yeah. So psychologists call it the incubation effect. Yeah. And I think that's right. So, when you see a problem, right, as you said, first thing you got to do is you got to play around with it a little bit, just try different things. And then the next step is once you've tried different things and you've hit the dead end, you've got to walk away for a little while. So I remember I was reading a book of journalism about mathematics. There's like journalists writing about recent discoveries in math. And I decided to go through and just highlight all the places in this book where the mathematician made the discovery. And it was, I could probably rattle off a bunch of them. One of them, it was while he was riding a train. Another one, brushing his teeth. Another one, the person was dropping their kids off at like a birthday party. Another one, at their kid's soccer game. Another one, walking around campus, going to get lunch. I mean, everybody made their moment of discovery not while they were working on the problem, right? Like the pieces clicked into place at some other moment in time, at some other place, not at their desk, not at their chalkboard, not while they were hunched over a PDF they'd printed out, but while they were just going about living their life, absorbed this problem, and then it was running through their mind and moving through their bloodstream. And that's when intuitive leaps happen, right? That's when you make connections, right? I don't know about you, but for me, like definitely out walking is a good place for ideas. Taking a shower, great time to get ideas. Sometimes I think I'm getting good ideas when I'm running, but I think I'm getting less oxygen to my brain then. When I get back, the running ideas are usually not that good, but walking ideas are good. So there's some optimal speed maybe to be moving to have good ideas, the perfect velocity. There's some philosopher, I can't remember who says you want to actually have a boring walk to get ideas. You don't want to be on like a nice walk around a lake you don't usually go to. You want to be like walking around the same landscape you're used to, because that sort of gives you a nice just background, like white noise for your thoughts. But yeah, I think that's, right. Having computers so ubiquitous in the world, we can kind of think of ourselves like computers. We're not that kind of computer. That is not how we work. We need breaks and we need a chance to breathe and different experiences to keep thoughts circulating in an interesting way.
That's why I'm guessing that in the mix of his solving of that problem for 7 years or getting close and then having the friend help, that he had other routines going on, and that was one component of revisiting over and over. But then it was like, okay, I have this class these days at this time. I have my regular routines.
Yeah. No, I'm sure that's true. Yeah. So Simon Singh wrote a great book called Fermat's Enigma about the history of the problem and about Weil solving it. And I've read that book and I've heard Weil speak briefly before. But actually, you're asking a great question. So I would actually love to hear you talk to him about like, what was the day-to-day routine of that time? Because there's something great. When I talk to other people who write books too, I love hearing what their writing routine is. You can't ever copy it because everybody's a little bit different. You gotta kind of sculpt your own patterns. But I'm sure you're right that whatever it was he was doing in that time, he needed probably a lot of pieces in place to keep himself sane while continuing to thwack his forehead against that problem.
I think, for people who are listening to this and they're hesitant about math, or they've felt disconnected from it at a time and they want to maybe enter in, we may have sparked some curiosity here. What's some piece of advice or encouragement that you'd offer, other than grabbing your book, which I'll link up to in the show notes, to help them see math in a new light?
First thing I would say is that math is thinking, sort of in its purest form. It's ideas. And so the part in school that you often see is almost math more as like a technical craft. It's more like knitting, where if you drop a stitch, you've kind of messed it up. And if you don't carry the 3, you've messed it up now. And so it's very much about kind of almost this physical product of the number on the page you're creating. For most people, for most purposes, math isn't really about that precise number. It's a way of thinking. And the other thing I would say, and I say this from experience, I don't just say this as someone who got a degree in math. I don't think everybody could do exactly the coursework I did, but I've taught middle school, I've taught high school, I teach community college now, and I've met so many people who think they can't do math, who can do wonderful math, who can solve problems, who can learn skills they didn't think they could learn. And the obstacle is almost always emotional more than it is cognitive. It's like that, whatever, different brains have different abilities. I would never make the NBA, right? Love basketball. There's nothing I could do to make the NBA. Most of us, there's nothing we could do we would never be Andrew Wiles, right? We're not going to solve that problem. But that's fine. Most of us don't need to. Like, I don't need to make the NBA. I can still get a lot of joy out of playing basketball. And most people can still get a lot of use and a lot of value out of the mathematics they learn. The obstacle, and this is actually what I asked this question to Andrew Wiles the time I got a chance to meet him. And I said, so like, what's the message you would give to people more broadly? What he said is, you have to learn to accept the state of being stuck. It's not, you've got to appreciate the beauty of math, although math is beautiful, or you've got to, learn how to ask people for help, although that's also really useful. You do. It's being stuck. You got to accept that it's okay to be stuck, and accept that not just intellectually, but emotionally. When you're in that stuck moment, to kind of quiet that anxiety response, this is okay. This is where I'm supposed to be. Like, I'm solving a problem. I'm not looking at a solved problem. And to be in the process of solving a problem is to be stuck. It's to not be quite sure where to go. And you got to try a direction anyway and see what you can learn about the landscape of the problem.
Yeah. Trying and seeing if something works. It's scientific experimentation in a sense as well, right?
I don't often feel very scientific when I'm doing it. Often I feel like and actually one of the ways you've done a great job with a math problem is when you get to the answer, you're like, oh, that was obvious. I feel so stupid not having seen that. And the thing is, like, we all feel that way when we solve a problem in a math class we're taking, but also mathematicians feel that way. There'll be, one of those open problems that's stuck, where the guy who solved the problem while was brushing his teeth. There was a problem that had been open in statistics for 40 years. And when everybody saw the solution, they were like, oh, that's obvious. It's like, well, no, it wasn't obvious. It took 40 years.
It's a little disheartening
his teeth.
Yeah, it's a little disheartening to have that feeling over and over again as part of the reward baked in, right?
Yeah, I mean, I guess the flip side of it is the simplicity of it. The fact that you can then hold the idea in your head, look at it and be like, that's the thing I was seeking. And it's kind of lovely to have a little jewel you can hold like that, as opposed to the thing you were seeking be something so complicated. You're like, well, I found it, but I don't understand it.
That's true. I solved that one, and that one was so obvious. So spin it. Don't just, that was so obvious. Yeah. And I'm so stupid. No, it's, that one was so obvious. So that means this one can't be that much harder than that one. At least at first glance, motivation, use it as a motivator instead of
use it as a motivator. And also that, like, it can be hard to rewrite your own sense of what's a reward, but really to see it as like that, the fact that you see it as obvious now means you really mastered that problem. You really saw it. And Wiles has this beautiful analogy he would give where when he was working on part of the problem, to him, it felt like stumbling in a room full of furniture. The room is totally dark, though, so he was like bumping into stuff and he's banging his shins and getting bruised and no idea what's going on. And then finally, he said about every 6 months, he'd find a light switch and he'd flick it on and then, that's what I was working on. That's what I bumped into. That was an ottoman. That makes sense. That was the couch. I didn't realize it was a sectional couch. That explains why I couldn't get around it over there. And so suddenly that part of the problem he'd been working on would become illuminated to him once he'd kind of banged around on everything. And then he'd open the door to the next room and that one would be dark too. And then he'd repeat the whole process for the next 6 months. So, luckily, most of our lives don't demand that level of patience from us. But in microcosm, they do. There will always be times when we're confused and you come out the other side and it all feels simple. I mean, I guess but the word for that is wisdom, right? Like, I think wisdom feels obvious to the wise. And so if something feels obvious to you and once it didn't, there was a time when it didn't feel obvious, you had no idea this was true. That's wisdom, not a bad thing. It doesn't mean you were a failure before. It means you've learned something about the world.
The more you navigate dark rooms with lots of furniture in them, the better you get at doing it the next time around. Or knowing an estimated time of reaching a switch that then suddenly, okay.
Yeah, no, exactly. I've never thought about doing it with an actual room full of furniture, but, that might be a good kind of trust building exercise with yourself.
It's a good example for, it's one of those trust building exercises for a team. Yeah. It's like, okay, I'm over here. Okay, I don't know. Where are you? It's an escape room at a whole new level.
Escape just from an ordinary room.
Yes, escape from an ordinary room. Just there's no lights and lots of furniture.
That's right. Yeah.
That's what life feels like sometimes. Well, I would love to point people to where they can find out more about. You've got multiple books. You've had books previous to this. I'm sure you'll do more. Where can people go to do that?
Yeah, so my website is mathwithbaddrawings.com, and that's my brand title. And that comes, the bad drawings comes from a very authentic place, which is I really can't draw, but I write about math and I teach math. So math is very visual, right? You really benefit from visuals. So I just draw anyway, even though it's really, really not my strength. My first book was Math with Bad Drawings, and my blog is titled Math with Bad Drawings. You can find me that same on Facebook and Instagram, and as of right now, when I'm speaking, I'm still on X/Twitter, although I don't know how long that'll last. Social media comes and goes, but the blog, I've got that URL locked down. So mathwithbaddrawings.com should be there forever.
Perfect. Yeah. So Ben, I'll link up to that in the show notes. And I really hope that this is something that kind of is intriguing and fun and, scratches an itch for some people that, and maybe I may have triggered some people too with my story or something along those lines.
I was going to thank you for me to talk about math, because I know it's not everybody's favorite way to spend a Friday afternoon is chit-chatting about math. But I appreciate if we can open those doors for more people. I think people will be excited at what possibilities they can find and what paths it opens up in their life if they can stop just kind of instinctively moving away from any door that's got math written on it.
Yeah,
I appreciate your
it's a limit that I think is too limiting, and it definitely did that to me, and I'm glad that I'm kind of past that now. Hopefully others can get some encouragement here. So Ben, great talking with you.
Give people a foot over the wall if they can, wherever they need it.
Yeah.
Thanks so much.
Great. Thanks for being here. Well, that's another podcast crossed off your listening to-do list. I hope that you found new insight in this conversation when it comes to math and math as a language. And identified some of that stuckness that you might have felt. I know for me, sometimes a problem can be something you're stuck in and a solution can be hard to find. But as long as you're embracing that stuckness and going about your creativity and your problem-solving techniques and even finding answers subconsciously in the mundane as you go about other things and come back to it on a routine basis, you'll still be able to solve those problems or figure out, and maybe with help, that it's unsolvable, and that's okay too. If you found this episode helpful in any way, I would love for you to do me a favor and share this episode with somebody you know needs to hear it. Hit that share button in your podcast player app of choice. Send it on over to them. Let them know about it. That'll really help share the show. Thank you so much for sharing. Thanks again for listening, and I will see you next episode.